Hiya, pirates. Welcome to the thermodynamics section of the year. A lot of this we're going to go through fairly quickly because you've had this already. So we're going to drink from the fire hose of knowledge, as they say, because this one lecture will end up being basically everything that you spent time on in first year chemistry learning how to do. So whether you were in regular chemistry or accelerated chemistry, this is going to be pretty close to everything that you learned in that whole unit, 2, 3, 4 week unit in one lecture here. So we're going to go through this stuff fairly quickly. If you are lost or confusified by any of it, you'll have to let me know, and I'll be happy to go through things a little bit more slowly with you. But what we're going to try to do is hit the highlights of how to do all of the math in all of the basic ideas here for heat and temperature and calorimetry, and how to do all of that. So think back to your first year of chemistry, and there should be some help. Have a calculator handy, and let's go through this. So one of the most important things for us to know is that there is a difference between heat and temperature. Temperature is simply a numerical measure of how hot or cold something is. It is basically the measure of the average kinetic energy of the molecules that are in the sample, or if you want to put it another way, it is the speed of the particles, the average speed of the particles. If you are at a hot temperature, then you have particles that are moving very fast. If you have a cold temperature, then you have particles that are moving very slowly. You use a thermometer to get that, and we're usually talking Celsius, Fahrenheit, or Kelvin there, usually in Celsius, although some of the stuff that we're going to end up doing is going to have to be in Kelvin there. Temperature is like the value of a coin. So if this is 1 cent, if this is 5 cents, and this is 10 cents, and this is 25 cents that is there, I want you to think of temperature as if it was each of these coins' values that was here: 1 degree Celsius, 5 degrees Celsius, 10 degrees Celsius, and 25 degrees Celsius. As you go up and up and up, as far as your increasing value, you are talking about increasing kinetic energy on average, or increasing speed of the particles on average that is there. So on average, a 25 degrees Celsius sample, the particles are moving on average faster than 10, than 5, than 1 that is here. So temperature is really just like the face value of a particular coin. What then is heat? Well, heat is the total of the energy that is in a particular sample, the total of it. Well, how are we going to get more than just the temperature? Because if the temperature is how hot it is, isn't that the same thing as heat? No, it's not. Temperature is basically just a measure of how fast the particles are moving. Heat takes into account all the factors which affect these things. Think about how a thermometer works. If you take a thermometer and you stick it into a beaker of water, the reason that that thermometer goes up is because the area right around that thermometer, the particles that are there are hitting that, bouncing off of it, and transferring its kinetic energy. And that then is going to cause the alcohol or mercury in the thermometer to go up the tube. But that thermometer has no concept of what it's in. It doesn't know that it's in water. It just knows that particles around it are slamming into it. It also doesn't know how many particles total are in the sample. If I were to take that same thermometer and instead stick it into a lake, right? So here's a boat floating around in the lake. That thermometer would have no concept that it is sitting inside a giant lake or swimming pool or something. Again, all it knows is that the particles that happen to be right around it have a particular speed. It doesn't know that it's in water, and it doesn't know how much water there is. So to take that into account, heat, we have to take all factors into account, of which temperature is just one. And there are 3 factors which determine the heat. 1, 2, 3. The first one is the temperature. Sure, as the temperature goes up, the heat goes up. That's pretty obvious. But number 2 is the mass. How much of it matters? So think about this. If I have a stack of coins here, sure, this stack of coins is worth 25 cents on average per coin, and this stack is worth 10 cents on average for those coins. But it's pretty obvious that if we add up all of the value here, the total value here is actually going to be greater than the total value over here, because there are simply more of these dimes that each individually add up to be more than the quarters over here. So if this is temperature instead of values, if this is 25 degrees Celsius versus 10 degrees Celsius, if we're talking about the speed of the particles, the quarters are more. 25 degrees Celsius is more than 10 degrees Celsius. But if we're talking about the total heat, the total value of this, then the total heat of the dimes is going to be more than the total heat of the quarters, because the overall value of them is going to be greater than the overall value of the quarters. If you have a cup of hot coffee and compare it to a cold lake, the cold lake has way more heat in it than a tiny cup of hot coffee. Even though the cup of coffee is hotter, its particles are moving faster. Now, if that's not bad enough, not all money is the same. So I've got a $100 stack of American bills and I've got a $100 stack of Canadian bills. These guys are not the same. Even if the mass or amount of each of these guys was identical, even if the stack here of bills was the same as the stack here of bills, and even though their face value is the same, 100 versus 100 here, they are not worth the same, because Canadian money and American money have different intrinsic values. So that is likened to our third factor, which is specific heat capacity. Specific heat capacity. The substance itself matters. So if we want to figure out what the total heat of something is, then we need to know 3 different things. We need to know what its temperature is, we need to know how much of it there is, and we need to know what it is, because different substances have different abilities to absorb or emit heat. Which is why when you have, for instance, a pot or pan, the cook surface of it might be made of metal, but the handle of it might be made of wood, because metal and wood absorb and emit heat differently. They have different specific heat capacities that are there. So, overall, temperature is just a measure of how fast the particles are moving, or a measure of the average kinetic energy of them. We have seen these graphs before in previous ones. If you're talking about something that is cold, like this 100 Kelvin sample here, there is not a very wide distribution of molecular speeds, and you have a whole lot of particles that are at this average speed here, which is right around here. So if I were to take the average of the particles in the 100 Kelvin sample, that would be the average of the 100 Kelvin. If I were to then increase it to the 1000 Kelvin that is here, which is my red line that is here, you can see I have a much wider distribution of molecular speeds. I got a whole bunch of them up here that are going way faster. And not only that, but my average velocity, which is going to be somewhere around here, my average velocity at the 1000 Kelvin is going to be much faster than the average velocity of my 100 Kelvin, which is going to be way down here. Okay? So that's temperature. Heat is split into 3 different factors: mass, specific heat capacity, and temperature. And heat usually gets the symbol Q. So Q is equal to MC delta T. All of this should be old news to you, or again, if you prefer, Q is equal to MC TF minus TI. So sample 1 says how much heat is needed to raise 50 grams of water, and I gave you the specific heat capacity, from 10 to 70 degrees. So what do I want? I want the heat, so that's going to be Q. And my mass is going to be 50 grams because I have 50 grams. My specific heat capacity is 4.184 joules per gram degree Celsius, given to me right there. So it takes 4.184 joules to raise 1 gram of water by 1 degree Celsius. That's what that means. And then my temperature change is going to be 70 minus 10 because that's my initial and that's my final there. And that's degrees Celsius. So you take all of these factors and you plug them into your equation. Plug them into your calculator here, and I'm getting about 12,552 joules, or if we change that to 3 significant figures, that looks like it's going to be about 12,600 joules to 3 significant figures. Sample number 2 says how many grams of copper can be raised from negative 30 to 22 with 80 kilojoules of heat. Ooh, first of all, be aware there, that's 80 kilojoules of heat. So what we're talking about there is 80,000 joules. And why does that matter? It matters because the specific heat capacity was given to you in joules. So, that's my phone. Yes, my ringtone is the Phineas and Ferb theme song. Sorry about that, guys, but I'm not starting over. All right, so not the Phineas and Ferb theme song. It's the Doofenshmirtz thing. Look it up. Look it up, Joe. All right, so anyway, 80,000 joules is the amount of heat that we have. Again, you got to make sure that your units match. I've got joules and joules. Now, if this were in kilojoules over here, you could have left the 80, but it is not. So I've got 80,000 joules, and I want to know the grams. So in this particular problem, with Q is equal to mCTF minus TI, the M is what I am looking for. So the 80,000 is my Q. My M is my X. I don't know what that is. Copper has a specific heat capacity of 0.385 joules per gram degree Celsius. And I want to raise it from negative 30, that's my TI, to 22, that's my TF. So this is 22 minus negative 30 degrees Celsius. So if you do the math on that, so 22 and 30 is 52, so then that's 80,000 divided by 0.385 divided by the 52. Looks like I can do about 39.96 grams. So 39.96 grams, or to 3 significant figures. Oh, look at that. We have a goofy situation here. That would be 4,000 grams, but that's only 1 significant figure. So 4.00 times 10 to the 3rd grams. That now gets me 3 significant figures. That's there. So about 4,000 grams of copper there. All right, phase changes. When you heat up a substance and that substance goes through a phase change, either boiling, melting, freezing, condensing, any of those things, you'll notice that the temperature stays the same during those phase changes here. And if the temperature stays the same from here to here, but we know it requires energy to boil something, then we cannot use Q equals MC delta T, because the delta T would be equal to 0, and that would imply that it requires no energy to boil something, because M times C times 0 would give you a 0 value, and so that doesn't work. So what we're going to need now is we're going to need a new equation here. And our new equation is called the latent heat. The latent heat. And it is the energy involved in a phase change. There are 2 of them that will probably come up, although technically there are 3 of them that exist. The 2 of them will come up is fusion and vaporization. What are they? Fusion is melting or freezing. And please note that melting is the same thing as freezing, except it's in the opposite direction. So it all depends on if you're talking about going from a solid to a liquid, or are you talking about going from a liquid down to a solid there. Melting and freezing are the same thing. That's L of F. That's heat of fusion. And our second one that we have is the heat of vaporization that is here. And the heat of vaporization is the energy that's involved in boiling or condensing. So boiling is the process of going from liquid up here to gas. That's boiling. But if you were to take heat away and take a gas and turn it back down to a liquid, then that would be condensing. That would be condensing. That would be the process of L of V. That is the heat of vaporization. And since there is no temperature change at those aspects, we have a new equation. And our new equation is as follows. Q is equal to L of F times the mass. That's for melting or freezing, because the temperature is no longer there. So it's like MC delta T, except there is no delta T, and therefore we've got to have a new value that's like our identity factor, and that's what the L is. You might say, what the L? So these are our new equations for boiling, condensing, melting, and freezing. It's just going to be L of F times the mass, or L of V times the mass. It's very, very simple. So coming back up here to these guys up here, we are going to have to take into account multiple factors, probably three different factors. The first factor is that you have solid, liquid, and gas. And please note that the solid, liquid, and gas have different specific heat capacities. So solid ice has a specific heat capacity of 2.1. Liquid water is your 4.18 or 4.2. And steam has a value of 2.0. So that's factor number one. All of those are going to be different. Factor number two, you're going to have melting, where we're going to have L of F times M, or boiling, where you're going to have L of V times M. And then, if that's not bad enough, please note that the boiling and the melting points are different from substance to substance. So water freezes at 0, right there at 0, and it boils at 100, right there. Iron, if we were to do that, iron has a different melting point and a different boiling point. Iron doesn't melt until 1538 Celsius, and it doesn't boil until 2861 degrees Celsius. So if you were to use 0 and 100 for iron, you'd be way off, because iron is a solid all the way up to 1538 degrees Celsius before it melts. And then you have molten or liquid iron. Please note that solid iron has a different specific heat capacity of liquid iron. I couldn't find gaseous iron. If you're talking about gaseous iron, you're probably talking about the heart of the star or something, not something that you would experience in normal lab circumstances. Heck, you probably don't even get up to this point in either of these guys, but it's a lot easier to conceptualize than gaseous iron. Yeesh. All right, so anyway, we've got a lot going on in these problems. The basic idea, though, is as follows. Let me be clear about this. If you are talking about doing a problem in this segment, or this segment that I'll leave in blue here, then you're going to have to use Q equals MC delta T for that segment. But be very careful, because as we showed up here, you cannot do it all as one big thing. You have to do it as three different sections, because our first section here has that specific heat capacity. Our second section here has that specific heat capacity, and our third segment here has that specific heat capacity. So you have to split it up into three different segments and look at just what is happening in each individual segment. This, and this, and then their temperature changes at each individual step. So you have to treat each one of those blue sections as its own problem. And then you have to take each of these pink sections that's here, and you have to use L of V or L of F L of V there, and L of F there. So you were talking about potentially a 5-segmented problem where you have to use your L of F here and your L of V here. So what do these problems look like? Well, let's take a look here. Sample 1. How much energy is required to melt 50 grams of zinc at its melting point? Okay, all we're trying to do now is melt zinc. Well, that's easy to do. So what are we going to do? We just want to melt zinc. So Q then is going to be equal to L of F times the M. So the L of F is 112 joules per gram times the mass, which is 50 grams. So this was a very straightforward problem. 112 at 50 is about 5,600 joules. Very easy. So that pink right there, if I were to do that, would just be this segment right there, the melting segment. That's all we did, is that flat segment there was we melted it. Question 2. How much energy is required to boil 3.5 moles at its boiling point? Please note that now we're in moles. Does that match our value over here? Yes, it does. Okay, so they gave us the L of V in a per mole, and then they gave us moles. We're fine. We can use our equation. So Q is equal to L of V times the M, which is actually moles in this case. It's fine. So the Q is going to be 10.2 kilojoules per mole times 3.5 moles. We're all good. 10.2 at 3.5 is about 35.7 kilojoules for that. So that's good. We are all good to go there. Sample 3. And again, if we were looking to that here, that would be just this segment here. So that would be just, all we did was we boiled some chlorine. Okay? Sample 3. How much energy is required to be given off to solidify 75 grams of iron at its freezing point? So all we're doing is we are freezing. Now, I intentionally did this to trick you because you are going to not pay attention to the units, and the next thing you know, you are going to get the problem wrong. So please note that this is in grams and this is in per mole. It's easy enough to change one to the other. I don't care which, but you got to make sure that your units match. So if I'm going to do this, then I'm going to take my 75 grams of iron and I'm going to look it up, and I'm going to find that it's 55.85 grams per mole. So 75 divided by 55.85 is going to get me about 1.34 moles. So just be aware that they might be mean to you in these problems, and they'll give it to you in one unit here and a different unit over there. You just got to be careful to check that out. So the Q here is going to be L of F times M. So your L of F is going to be 14.9 kilojoules per mole. And then I'm going to have 1.34 moles over here. And so then 14.9 at 134 gets me about 19.97 kilojoules, or 20 kilojoules to 3 significant figures. That would be 2.00 times 10 to the first kilojoules. I wanted to get it to 3 significant figures. All right. So these 3 problems here, all we did was we did this horizontal section here or here. But as I said 5 minutes ago, they could very well give you problems that they expect you to go anywhere up and down the ladder on this thing. They could ask you to go up and over. They could ask you to go over and up and over, right? It all depends on the particular problem, and you have to be ready to know that each of these segments is going to be different. So, once again, the solid that is here, that goes to the liquid that is here, that point and that point where I freeze or melt or vaporize or condense is going to be different for every substance, and you are going to see different C's here, here, and here, right? And please note that this is the same thing except in reverse. So if you start hot, then your gas condenses to a liquid, goes down to its freezing point, then it freezes, and then it can go down lower than that. So sample 1 says, how much total heat is needed to be given off if 3,000 grams of steam at 250 degrees Celsius are cooled until every bit of it is turned into ice at negative 40 degrees Celsius? Wow, okay, so this is going to be significant. Let's do some labeling here first. So first of all, I'm starting up here at 250 degrees Celsius. Then I'm going to go down, over, and down, technically speaking. So where is the boiling point here? Where does steam condense down into liquid water? Well, that's at 100 degrees Celsius, all right? So my step 1 that is here is Q equals MC delta T. And so my Q is going to be equal to 3,000 grams times the specific heat capacity. Now, careful, it's not 4.18, it's not 4.2, because this is steam. It's not liquid water. And so because it's steam, then that's going to be 2.0 joules per gram degree Celsius. That's this here. It's steam. And we are changing by negative 150 degrees Celsius. So the Q for my first step here is going to be 3,000 at 2 at 150 is 900,000 negative, or negative 900 kilojoules. There. That's step 1. Now what has to happen is we have to do step 2. I'll put step 2 in a different color here. Step 2 is this stuff has to condense. So that's going to be Q is equal to M times L of V. So the Q for that step is going to be 3,000 times the L of V, which is 2260 joules per gram. So that's going to be 3,000 times 2260. And if I convert that into kilojoules, that is 6,780 kilojoules to do that step. Now we'll do a different color. Now we'll do this red that's here. Now I'm at liquid water, and I have to go from 100, and I have to go down to its freezing point, which is 0. So this is Q equals MC delta T, right? And so Q is equal to 3,000 times 4.2 joules per gram degree Celsius. Again, now we're talking about water that's here. So that's 4.2, and I'm going to change by negative 100 degrees Celsius. So that's going to be 3,000 at 4.2 at 100 divided by 1,000 to get it into kilojoules. I'm talking 1,260. It's going to have to lose negative 1,260 kilojoules. By the way, I just realized I made a mistake. This guy here, it has to lose that amount, so don't forget the negative sign over here, because it has to lose that energy to do it. So it's got to lose negative 600, it's got to lose 6780 kilojoules to do that. My bad. 2 more steps. Our step here is the freezing process. So that is going to be Q is equal to L of F times M. The L of F is up here, and that's 333 joules per gram. And again, I have 3,000 grams. So 333 at 3,000 gets me 999, negative 999 kilojoules. It has to lose to do that. Last step is this guy here. So I have to cool a solid. So that's now back to Q equals MC delta T. So that's going to be 3,000 times my new specific heat capacity for the ice. So the specific heat capacity for my ice is up here at 2.1. So that's going to be 2.1 joules per gram degree Celsius. And then I want to go from 0 degrees Celsius all the way down to what? Negative 40, it said. So I need to go all the way down to negative 40. So I have to lose 40. So that's going to be 3,000 at 2.1 at negative 40 is negative 252 kilojoules there. Wow, that problem was involved, and we're not even really done yet. Step 1, negative 900 kilojoules. Step 2, negative 6780 kilojoules. Step 3, negative 1260 kilojoules. Step 4, negative 999 kilojoules. And step 5, negative 252 kilojoules. So add that all up. 6780, 1260, 999, and 252. That's negative overall 10,191 kilojoules that have to be lost in order for this reaction to. Problem number 2 is very, very, very similar to problem number 1. The only difference is that instead of dealing with water like we see here, we are going to be dealing with bromine. And instead of cooling it like we did in problem number 1, we are going to be heating it. That's here. And instead of all of the information being given to you in a per gram basis, as it was here in our first problem, it is being given to you in a per mole basis, which is here. So again, really fundamentally speaking, though, the problem hasn't changed. Some of the particulars have changed, but if you watch closely, it really shouldn't be that big of a deal. Now, they did get a little goofy with you. They gave you 70 grams of bromine, and again, all of these units here are in moles. So you have two choices. You can either take all of these units that are here and turn them all into a per gram, right? And you'll have to do that 5 times. Or you can just take your 70 grams of bromine and turn it into moles and then do all the problems just like we did before. So that's what I have chosen to do here. So on this one, what you've got is bromine, which weighs 79.9, but it's twice because there's 2 of them there. So that makes it 159.8 grams per mole, which means that instead of having 70 grams of it, what you really have is 0.438 moles. 0.438 moles of it. And so that's the unit that you are going to use for the rest of these problems. Now, remember, up here for water, our important points were here at 100 and here at 0, right? Except that in this particular problem, we don't have water, so we don't have 0 and 100 anymore. We have these points, -7 and 59. So bromine actually melts and freezes at -7 degrees Celsius, and then it boils at 59 degrees Celsius. So what you're going to do is you're going to have upwards of 5 different steps that you're going to have to do for each of these guys here. You have to heat a solid, and then you have to melt it, and then you have to heat a liquid, and then you have to boil it, and then you have to heat a gas. So let's see what they want us to do for each of these guys. It says that we want to go from -80 up to 125. So we're going to start down here at -80. And where is 125? Yep, 125 is above 59. So yeah, you're going to have to not only get it up to its boiling point and boil it, which is here, but then you're going to have to get it hotter, so that's 125. They could have said, let's go from -80 up to, I don't know, 30. So if they had said 30 degrees Celsius, then you would not have had to have done this step or this step here, because 30 degrees Celsius would just get it to the liquid phase. But that's not the case. The case is that we want to go from negative 80 all the way up to 125. So we're going to do this in 5 different steps. So step 1 here, we are going to heat up a solid. When you heat a solid, you use the equation Q equals mc delta T. So our Q is going to be equal to, what was that number? 0.438. So our amount is 0.438 moles. Specific heat capacity, we're talking about solid bromine here. So according to this information, the specific heat capacity of solid bromine is 0.037 kilojoules per mole degree Celsius. 0.037, and that is already in kilojoules per mole degree Celsius. And now what's our temperature change? Again, one of the biggest mistakes that students make with these problems is they go, well, I want to go from 80 and I want to go up to 125, so that's a temperature change of 205 degrees Celsius. Yeah, but it's not changing 205 degrees Celsius as a solid. It's only going from negative 80 up to negative 7 as a solid. So the 205 is our overall number, but that's not what it is at each individual step. And right now, all we're doing is heating our solid. So we're going to go from negative 80 up to negative 7, so that's what, a 73 degrees Celsius change. So I've got 0.438 at 0.037 at 73. So that gets me, the Q for my first step is about 1.18 kilojoules for that step. All right, now I have to come over here and I have to melt it. So I'll make that one purple for whatever reason, because that was the color that I saw. So when you are melting something, you no longer have delta T, and so we're back to heat of fusion. So this is just going to be Q is equal to L of F times M. So my Q then is going to be equal to the heat of fusion that they gave. Oh, there it is. They told us that the heat of fusion of bromine is 529 kilojoules per mole. Okay, so I'm going to come down here, and that's 5.29 kilojoules per mole, and it was that same number, 0.0438 moles, because it's always going to be the same amount. Nope, not 0.0438, 0.438, my bad. Almost made a mistake there. Try that again, sorry. 0.438 moles. Check your references. All right, so Q is equal to 529 at 0.438. That gets me about 232. 2.32, and that's in kilojoules there. All right, so that's step 2. Now what I'm going to do is I'm going to heat up the liquid bromine. So that's going to go from here up to here. And so we're back to temperatures changing again. So this is going to be Q is equal to mc delta T. So my mass is still the same, 0.438 moles. My specific heat capacity for liquid bromine, there he is, 0.075. So this is going to be 0.075 kilojoules per mole degree Celsius. And then how much is it changing? Well, it's going from a negative 7, which is here, up to 59. Whoopsie. Negative 7 here up to 59. So that's what, 66 degrees? So that's 66 degrees Celsius there. So I've got 0.438 at 0.075 at 66 is 2.17. So my Q here is 2.17 kilojoules when I round that off. So that's step 3. All right, now we're here at step 4. I'll make that my blue step. Now we are boiling. So when we go to boil something, that is back to our latent heat equation. No temperature is involved. So Q is equal to L of V times M. So I can look those numbers up. There it is, the heat of vaporization of bromine, 15.4 kilojoules per mole. So that's easy. 15.4 kilojoules per mole. times 0.438 moles. So that gets us 15.4 at 438. 675. 6.75 kilojoules. So that's for step 4. And then finally, we are starting here at 59 degrees Celsius, because again, that's where this stuff boils. And I want to get up to 125 up here. So my last step up here is back to a temperature change problem. So this is going to be Q equals MC delta T. So Q is going to be equal to my 0.438. Change my font size here because it's getting to be a little tight. Q is 0.438 moles times the specific heat capacity, C, of the gas now. So that is apparently 029. So the specific heat of the gas is 0.029 kilojoules per mole degree Celsius. And what are we doing? We're going from 59 up to 125. So 125 minus 59 gets us another 66 degrees Celsius. Look at that. How curious is that? All right. So then my Q is going to be equal to 66 at 0.029 at 0.438 is 0.838 kilojoules for step 5. So now I go ahead and I look up all of my finals. So my finals are 838, 675, 217, 232, and 118. So if I take all of those, 118 for step 1, 232 for step 2, 217 for step 3, 675 for step 4, and then 0.838 for the final step, gets me about a 13.3 total kilojoules. So the overall process for this whole shindig here is about 13.3 kilojoules for this whole thing. So yes, it's labor intensive. Yes, it's a pain because you have to do 5 different problems, really 6 by the time you add them up, maybe even 7 by the time you take your grams and turn them into moles. But to be honest, each individual step is not terribly difficult if you keep track of all of the numbers. And there are a lot of them that are here, right? Just out of completeness' sake, remember that 205 that we were talking about before? Remember him? Well, let's just double check. We went from negative 80 up to negative 7. That was 73, right? And then we went from negative 7 up to 59. That's another 66. And then we went from 59 up to 125. That was another 66. If you add all of those temperature changes up, you get 205. So overall, the whole thing changed by the 205. But nowhere do you actually use the 205 because you're not changing 205 as a liquid or a solid, 205 as a liquid, or 205 as a gas. You are changing a total of 205 degrees, but you are changing it in different segments, which is why you have to do this and break this up into so many different pieces. Last thing to say about this is that I don't know that they're going to give you anything as excessive as this problem. This is probably well above and beyond the Call of Duty as far as what they would expect from you. But what they could easily have you do is like the brown and blue steps here. How much does it take to raise something to its boiling point and then boil it? Or the other way around. How much does it take to raise something to its melting point, the orange, and then the pink there, the purple there, melt it? 2 steps. I don't know that they're going to go anything beyond that on the AP test. That would, again, be a little excessive, I think. But they could ask you any one of the combinations of these fives. 1-step, 2-step, all the way up, theoretically, up to all 5 steps. All right, so quick review of what we have done so far. And again, I apologize for the length of this video. Please keep in mind what we're doing here is I am in one video refreshing you about everything that you were supposed to have learned in your entire first year of chemistry about this topic. So this video is probably going to end up being nearly an hour. The other ones, I promise, will not be that long. All right, so I apologize for that, but I'm cramming all of the old stuff into one video here. All right, so we've got the differences between heat versus temperature, right? We've got the differences for phase changes, for latent heat. We have combined all of them together into big old problems like this with combination problems. The last question that you should be asking here on this particular topic is, where in the heck are these numbers coming from? Where did they make these numbers up from? Are they just making them up? How are they getting these numbers, like the 2260? Or how are they getting the 333? Or how are they getting the specific heat of bromine? How do they know that the specific heat of bromine is the 0.075 here for liquid bromine? Where are those numbers coming from? Well, it's a very simple answer. It's coming from the idea of calorimetry. Calorimetry is how scientists take all of the unknown values and turn them into known values. And they do it in a very, very, very simple way. They picked a standard. They picked one substance, just one, and they made up a number for it. And the substance that they chose was water. They completely and totally made up a number for water. And the number that they chose to make up for water was the easiest number that they can think of, which is the number 1. They said, you know what? Water, liquid water, has a specific heat capacity of 1. Now, that was for calories. 1 calorie per gram degree Celsius. All right? We use calories here for our food in America. It turns out that in other countries, they don't use calories. They use the metric version of this. And the metric version of this is the joule. And the joule is the same thing as a calorie, except it's a different number in the same way that Celsius is a different number for Fahrenheit, and so forth and so on. So the joule, all right, is the same thing as a calorie, except that the number for water is not 1. It is the number 4.184, and I'm not going to bother to go into why that is. Just know that that number is completely and totally and homogeneously made up. That number they made up. They said, you know what, we're going to make a number, and we're going to make up a number. We're going to keep it simple because water is prevalent. Water is everywhere. Water is easy to work with. You're probably not going to hurt yourself with water. We have a limitless supply of it. We're going to make it the number 1. And then later they changed it to metric with a 4.184. Don't ask why. Then what they did is they said, all right, what we're going to do is we're then going to compare all other reactions that we have. Everything else that we are going to do, we are going to compare it to that number. In the same way that if you consider the US dollar to be the standard, right? It may or may not be, depending on where you're from. If you consider the US dollar to be the standard, then you can compare other currencies to the US dollar, right? They did the exact same thing with this. They said, you know what, we're going to take the water and we're going to make it a specific heat capacity of 1. Then what we're going to do is we're going to do experiments like this. We're going to take some water and we're going to take a thermometer and we're going to put it in the water, and we're going to take something, and let's say it's something hot, like a piece of hot metal or something. And if you take and put a piece of hot metal in the water, that hot metal is going to give off heat. And as that hot metal gives off heat, it is going to be absorbed by the water itself. Now, we can't necessarily measure the metal directly, but we can measure the water. So whatever energy the water absorbed, the metal should have given off. So the heat lost is equal to the heat gained. Now, that is a very simplistic one, and it works for a lot of things. If you really want to get crazy with it, then you do what's called a bomb calorimeter, where you set it up like this, where you have a combustion chamber or some other thing going on in there, and all these things are pre-measured, and you take a sample and you light it on fire, and the heat that comes out here is absorbed by this container as well as the water in there, and all these things are pre-measured. We don't have this here at the high school level, although at the college level they probably do. I have taught classes at Harper before, and they have these devices, and you can get hyper accurate values for different substances by these combustion chambers. We're not going to do that. We're going to do this over here. In fact, I doubt that this even shows up on the AP test. You're probably going to look at very simple calorimeters like these open air, constant pressure calorimeters, styrofoam cup calorimeters, right? Coffee cup calorimeters. But the basic idea here is that if you know that you have in this sample a certain amount of water, you know the mass of the water, you know the specific heat capacity of the water, and with our thermometer here, you can measure the delta T of the water. So if you can know MC delta T, then you can know the Q of the water. And whatever happens in the water, whatever energy the water absorbs or emits, has to be equal to the same amount of energy that is either given off or absorbed by whatever sample it is that you put into the water. With one slight caveat. The Q lost has to equal the negative of the Q gained. There has to be an opposite sign in there, because you can't have Q lost be a positive number and Q gained be a positive. That doesn't make any sense. So mathematically, it doesn't work out. The terms lost and gained are implying the direction of the change of the heat, but mathematically, it doesn't work out unless you include a negative sign. Think about two guys. So here's guy number one, and here's guy number two, right? This guy's got a $5 bill, right? So this guy here says, hey, you need some money? No problem. I'm going to give the $5 bill to over here, right? Now, if this negative sign wasn't there, let's forget him for just a second. What just happened to this guy's bank account? Well, this guy's bank account went up by $5. If this guy's bank account also just went up by $5, well, then no one would ever be poor ever in the history of ever, because what would then happen is this guy here could just give the $5 back, and then this guy would go up by 5, and that guy would go up by 5, and this guy would just give the $5 right back over to here, and then the right guy would go up by 5, and he would. So it doesn't work that way. There has to be, in the exchange, one person losing and one person gaining. So if we go back to our original exchange here, so we start like this. Whoops, I think I had a bad day. So there we go. We go back to our original exchange that's here. If this guy here gives up $5 and goes over here, well, what happened to this guy's bank account? This guy's bank account went up by 5, but what happened to this left guy's bank account? It went down by 5. The guy on the left is actually $5 poorer than the guy on the right. Now, does negative 5 equal positive 5? It does not. So how do you make negative 5 equal to positive 5? You include a negative sign. And if you include a negative sign, then you have negative of positive 5. So now everything works out. So the point is that in calorimetry, you have the basic idea that any heat lost is going to be equal to any heat gained, except mathematically speaking, the heat lost and the heat gained have to include a negative sign for the math to work out. Now, you'll notice that I left those at Q. Why? Because you can do this in a number of different ways, and your Q's can be expressed in two different ways. We have seen Q in our previous problems as MC delta T, and we have seen Q in our previous problems as ML. So you could go MC delta T lost equals negative MC delta T gained. Or you could go MC delta T gained is equal to negative ML lost. Or vice versa. If you wanted to, you could go ML lost equals negative ML gained. It doesn't matter as long as you make sure that you take one Q and set it equal to the other Q, but don't forget a negative sign. And I like to put my negative sign on the right, but if you want to put it on the left, I don't care. All right, so let's take a look at a sample calorimetry problem. So here's what we got. I've got a 62-gram piece of metal that is at 97 degrees Celsius, and it's dropped into a styrofoam container that is containing 100 grams of water at 22 degrees Celsius. The final temperature of the mixture is measured to be 25.8. What is the specific heat capacity of the unknown metal? So let's examine what is occurring here. So first of all, let's look at these things from the terms of our water. All right, so let's go back to this and let's look at things from the terms of the water. So according to the problem, I have 100 grams of water. Yep, there it is. I know the specific heat capacity of water is 4.18 joules per gram degree Celsius. And what happened to the water? Apparently the water started at 22 degrees Celsius. That's where it's starting. So the water is starting at 22 degrees Celsius. Now, into that water, into that cup, I'm going to take a hot hunk of metal here. So here's my metal. And that metal, apparently, is 62 grams. It says so in the problem. And I don't know what the specific heat capacity of the metal is. That's X. That's X joules per gram degree Celsius. I don't know what the specific heat capacity is. That's my C. That's what I'm trying to get. So I don't know that. But apparently, I started it at 97 degrees Celsius. Maybe I put it in some water that was kind of boiling over here. But I'm starting it at 97 degrees Celsius. Now what's going to happen is you're going to take that piece of metal and you're going to put it into the water. And what's going to happen is that the metal is going to lose heat and the water is going to gain heat. And the amount of heat that the metal loses is going to be the same as the heat that the water gains that's there. So the only question is, where does it stop? Because the metal is going to get colder and the water is going to get warmer until they meet somewhere in the middle. And the problem quite clearly said that they meet in the middle here at 25.8 degrees Celsius. So the hot metal got cold. The cold water got hot until they met somewhere in the middle, and that was at 25.8. So the water went from 22 up to 25.8 degrees Celsius, and the metal went from 97 down to 25.8 degrees Celsius. All right, so now let's set these problems up. I know that the Q that's being lost by the hot piece of metal is going to be equal to negative the Q that's being gained by the cold water that's here. Now the metal, I know, is going to be MC times TF minus TI, right? So that's my piece of metal. And then that is going to be equal to negative, put it in brackets now, the water, which is again M times C times TF minus TI. So let's go ahead and plug in our numbers here. Well, the metal was 62 degrees. I'm sorry, the 62 grams. I don't know what the specific heat capacity is, so that's X. And now be careful. Everybody wants our numbers to be positive, but in this case, the number is negative. How do I know? Because the metal started at 97 degrees Celsius, and it ended at 25.8 degrees Celsius. So I went from 97 down to 25.8. I lost heat. So again, this number here should be negative for this, which is why we have final minus initial. So again, here's F and here's I here. So you always have final minus initial, TF minus TI. And then that is going to be equal over here to the mass of the water, which was 100, times the specific heat capacity of water, which is 4.18 joules per gram degree Celsius, times the final temperature, which was 25.8, minus the initial temperature, which was 22 degrees Celsius. And at this point, it's just math. So get out my calculator and let's do a little mathification here. 25.8 and the 97 at the 62 gets me on this side negative 4414.4 times x, if I'm doing my math right. And then that's going to be 25.8 minus the 22 at the 4.18 at the 100 is negative 1588.4, assuming I'm doing my math right. Now I divide this by 4414.4, and if you hadn't had those negative signs in there, you would have ended up with a negative number, which won't make any sense. So 1588.4 at the 4414.4 looks like I'm getting a value of 0.360 joules per gram degree Celsius there. So that was a long way to go for these problems. But in calorimetry problems, you're going to take one substance, you're going to put it into another substance, and you're going to measure the heat of substance 1 by actually measuring the heat of substance 2, which is almost always water. Doesn't have to be, but it almost always is water. But whatever heat that the one thing loses, the other one gets to gain. And all of it comes down to this equation here. Q lost equals negative Q gained. It's just a question of, do you use MC delta T as your Q, or do you use ML as your Q? All right, guys. So again, I know I went on for a very, very, very long time there. That was probably nearly an hour for this one. I promise the other ones in this are not going to be nearly as long. It will be much briefer. But again, what I just did there in an hour was try to catch you up on all of first-year chemistry thermodynamics. So I know that's a lot to do, and if you have any questions, by all means, please let me know. Because if you got tripped up by something up here in the first part, then something down here in the last part is not going to make any gosh darn sense. So please ask questions and go through the sample problems. And if you can go through the sample problems and get the answers right, then you'll be in good